Physicists recently did something strange. They built an experiment where light began behaving like electrons inside one of the most famous quantum effects in physics. At first glance, that sounds impossible. Photons carry no electric charge, so they should not behave the way electrons do inside a conductor. But in this experiment, light followed the rules of the quantum Hall effect, a phenomenon normally associated with charged particles moving in magnetic fields. The reason this works is not what most people expect, and it reveals something deeper about how physical systems behave. Welcome to the channel. If you're new here, I'm glad you found your way. This is a place where we explore science not just as a list of facts, but as a way of thinking about the universe. In this video, we're going to explore a fascinating idea in modern physics: how scientists manage to make light behave like electrons inside a quantum system, and why the result tells us something important about the role structure plays in nature. Section 1. The ordinary Hall effect. To understand why this experiment is interesting, we need to begin with a discovery from the 19th century called the Hall effect. Imagine a thin strip of material carrying an electric current. Inside that material, electrons move through the strip from one side to the other. Now place the strip inside a magnetic field. The magnetic field interacts with the moving electrons and pushes them slightly sideways. Instead of traveling straight through the material, the electrons begin drifting toward one edge. Charge begins to accumulate along that edge, while the opposite side becomes slightly depleted. This separation of charge creates a measurable voltage across the material. That sideways voltage is called the Hall voltage, and the entire phenomenon is known as the Hall effect. For more than a century, physicists have used it as a tool to understand how electricity moves through different materials. Section 2. The quantum Hall effect. In the 1980s, physicists discovered that under extreme conditions, the Hall effect becomes even stranger. When electrons move through extremely clean materials at very low temperatures and under strong magnetic fields, the sideways electrical response stops changing smoothly. Instead, it jumps in discrete steps. These steps are incredibly precise and repeatable. In fact, their values are tied directly to fundamental constants of nature. This phenomenon is known as the quantum Hall effect. What made this discovery remarkable was that the behavior did not depend on the messy, microscopic details of the material. Instead, it depended on something deeper: the topology of the system. Topology is the mathematics of structure, the way parts of a system connect and constrain one another. In topological systems, certain behaviors are protected by the overall structure itself, which means small imperfections cannot easily destroy them. Section 3. Why light should not do this. There is an important reason the quantum Hall effect normally involves electrons. Electrons carry electric charge, and magnetic fields can push charged particles sideways as they move. Photons, however, are electrically neutral. Light traveling through empty space normally has no reason to drift sideways like this. Because of that, light should not naturally produce a Hall effect. So how did physicists manage to do something that light should not be able to do? The answer lies in a clever idea that has become increasingly important in modern physics. Sometimes the mathematics of a physical system can be recreated, even when the particles involved are completely different. Section 4. Engineering a Hall system for light. In this experiment, researchers built a carefully designed optical system in which different frequencies of light interact in a structured way. Instead of electrons moving through a crystal lattice, they created what is essentially a synthetic lattice for photons. Inside this engineered environment, the photons behave as though they are moving through a system that mimics the effects of a magnetic field. When light travels through this structure, it does not simply move forward. The light begins drifting sideways. Even more surprisingly, the drift occurs in discrete steps very similar to the quantized behavior seen in the quantum Hall effect for electrons. The photons themselves have not changed. They have not gained electric charge, and the fundamental laws of physics remain the same. What changed was the structure of the environment through which the light was moving. Section 5. Why topology matters. Over the past few decades, physicists have discovered that topology appears in many areas of science. Researchers have identified topological insulators, topological superconductors, and protected quantum states that remain stable even when materials contain imperfections. Topological photonics extends this idea to systems involving light. In these systems, the behavior is stabilized not by delicate physical conditions, but by the global architecture of the system. When the topology is right, the behavior becomes remarkably robust. In many physical systems, stability does not come from strength alone. It comes from the structure of the rules themselves. Section 6. A cosmic perspective. This idea that structure determines behavior appears throughout the universe. On the largest scales, galaxies form along the vast network known as the cosmic web, a structure stretching across billions of light years. Black holes persist because the geometry of space-time allows event horizons to exist. Even the evolution of the universe itself follows constraints built into the structure of space-time. In cosmology, we often talk about forces and interactions, but beneath those processes lies a deeper principle. The structure of the universe determines which kinds of behavior are possible. In that sense, the photonic Hall experiment is a small laboratory example of a much larger idea. Physics is not always about what pushes things. Sometimes physics is about what the rules of a system allow to happen. Light in this experiment did not change its nature. Photons did not suddenly acquire electric charge, and the laws of physics were not rewritten. Instead, researchers created an environment where the rules governing motion were different. When the rules change, the behavior changes. The deeper scientists explore nature, the more they discover that structure matters, topology matters, constraints matter. Sometimes the most important question in science is not what pushes things, but what patterns the universe allows to exist. Once the structure is set, the behavior often follows naturally, from tiny photonic circuits in the laboratory to the vast structure of the cosmos itself. The universe seems to follow the same quiet principle. Persistence emerges from the rules of the system. I'd be curious to hear how you think about that idea. Thanks for sticking around. My name is Charles Carroll. If you enjoyed the video, consider subscribing, liking, or sharing it with someone else who enjoys science. Join me next time. Who knows where the science might lead us?